what I'd like to do is go over the strategy for a different series. Now that we have learned so many tests, we have 10 series. And first, I'm just going to quickly go through all 10 and talk about the strategy that I would use. Of course, any work that you submit involves full solutions and not just the strategy. So after we finish the strategy part, then I will go one by one and do the full solutions. Here we go. In this first one, if you look at this part without the minus 1 to the n, natural log of 2n over 3n plus 4, this goes to ln of 2/3 as n grows without bound. And so immediately, this will be term test because the terms with the minus 1 to the n part will oscillate. They will not go to 0. And we will be able to conclude diverges. Now, let's move on. Well, this is an alternating series. The terms are going to 0. Term test tells us nothing, but I see factorials, and so I'm going to do ratio test. And just as a comment, because we do in fact have an alternating series here, we can conclude absolute convergence using the ratio test. And we will see that this is what we conclude in this example. Now, moving on. Okay, these are quick. Strategy, strategy, strategy. Then we get into details. Number 3, well, what dominates the numerator and denominator is k cubed and then k to the 4th. And so I want to compare to, well, the sum of k cubed over k to the 4th, which is here. This is harmonic series, and this will diverge. But with this plus k minus 4, direct comparison would be a little challenging, so I will just say we will use limit comparison. But the initial strategy would just be, I'm going to use one of the comparison tests with the harmonic series. Now, next one, we see we have something all to the k here. This is 4 over k to the k. This is root test. Then for number 5, my numerator and denominator, what dominates is the same term, the 7 to the k. This is another term test. The terms in this case approach 1 as k grows without bound. Term test will give us diverges here. Be careful. Do not say by the term test converges, okay, because terms go to 0, terms go to 0, terms go to 0, okay, and you can't use the term test when the terms go to 0. The only thing you can use it on is when the terms do not go to 0, you can conclude diverges. Now in this one, number 6, this again is alternating. If I look at this, well, maybe I'll write the sum. We get 1 over k to the 0.7. Immediately, this is a p-series. It's a divergent p-series, in fact. So what I know, thinking so far, is this does not converge absolutely. But what I could do, and what I will do with the details, is come in with an alternating series test, and we will see this will converge conditionally. Number 7, well, this is not alternating. The terms, at least the numerators say, the numerator is either 2 or 8, depending on if k is even or odd. And in the denominator, I have this. I have a k to the 4th. So I am going to compare to the sum, k equals 2 to infinity of 8 over k to the 4th. This is a convergent p-series. And I will be able to use normal comparison here, comparison test. Maybe I'll write that. Now, we have some options on 8. You could make this work with one of the comparison tests. Me personally, my first reaction to this is I see a sum in the numerator. And so I'm going to write this as a sum of 2. They will be convergent series. And maybe I can write what they are here. When we have n cubed over n cubed plus 3 to the n, this is 1 over 3 to the n. And then when I have 3 to the n over n cubed plus 3 to the n, this is 1 over n cubed, okay? So one of them is a p-series, one of them is a geometric series, but they both converge. The sum of 2 convergent series converges. This is my strategy on number 8. Number 9, this is the only one on this list I would integrate, integral test. You might think you want to compare it to the harmonic series or the sum 1 over n squared. Neither of those will work so well because this series, maybe I'll write this as a note, and this is a good thing to think about as you're thinking about strategy. This series, well, the terms of the series sit between 4 over n and 4 over n squared, okay? So if we think normal comparison here, this part, we are bigger than something convergent. It doesn't tell us anything. And this part, we are less than, term by term, something divergent. It doesn't tell us anything. So this is the one time I would use integral test, and we can integrate the corresponding continuous function using substitution. We will see. U is ln x, du is 1 over x dx. Okay. So this is my strategy on number 9. The last one, this is geometric. My A, well, evaluate at k equals 1. We get 2 over 7. And the R is 1 over 7. This will be convergent. And we can find the sum if we need to, which we will when we do the detailed solutions, okay? So this is my strategy, quickly through 1 through 10. And this is what you want to practice enough so that you can get to this point when you're just looking at a series, immediately something comes to you in terms of the techniques to try. Now let's begin the detailed solutions. Number 1, just like I said, if we just look at here, without the minus 1 to the n, that part approaches natural log of 2/3, which is a negative number. And then for n large, really what's happening is we are the terms are bouncing back and forth between close to ln 2/3 and absolute value ln 2/3, okay? And this is why we use term test. So the limit as n goes to infinity, minus 1 to the n, ln of 2n over 3n plus 4. This does not exist because oscillates. And by the term test, this series diverges. So this is the detailed solution for number 1. Number 2, as I mentioned, this is alternating, and for me, I see factorials and I think ratio test. So we take absolute value, an plus 1 over an. Well, in this part, when you take the absolute value of minus 2 to the n, you get 2 to the n. So here we have 2 to the n plus 1 over, we have n plus 1 factorial, and then divided by 2 to the n over n factorial. Now, when I invert and multiply, I line things up. So we have 2 to the n plus 1 over 2 to the n, and then in the numerator, we have an n factorial, denominator n plus 1 factorial. Now, what will cancel is I have a 2 up here, and then n factorial over n plus 1 factorial is just n plus 1. And this is as simple as I can make it, but I'm ready to take a limit as n goes to infinity of absolute value an plus 1 over an. This is a limit as n goes to infinity of 2 over n plus 1. And if you think about this, fixed numerator and the denominator is growing without bound, this limit is 0, which is less than 1 by the ratio test. This series converges absolutely. Number 3, well, as I mentioned, this looks like the sum k equals 2 to infinity of 1 over k. And this is the harmonic series, or you could say it's a p-series with p equals 1 less than or equal to 1. This would be fine in terms of justification, but this diverges. Now, I'm going to do limit comparison because in order to use normal comparison with the harmonic series, I would need it to go like this. And then the terms here, the k cubed plus 1 over k to the 4th plus k minus 4, okay? I need to be greater than a divergent series in order to conclude diverges. But with this here, that's hard to say, right? Because smaller denominator, bigger fraction, bigger denominator, smaller fraction. So the normal comparison test is a bit challenging to me. I'm just going to use limit comparison. It's much easier here. And here we take the kth term of one series divided by the kth term of the other series. And if this limit is finite and positive, then both series have the same behavior. And in particular, in this example, we would conclude diverges. Okay, so when I invert and multiply, my numerator becomes k cubed, or k to the 4th plus k. Okay, now what's this limit? Well, we can see the limit is 1, which is positive. And so, limit comparison we get this series, k cubed plus 1 divided by k to the 4th plus k minus 4, well, diverges. This is the end of number 3. Number 4, root test. Root test. Okay, so let's look at the kth root of absolute value ak. Now in this situation, this is a non-negative series, so the absolute value I don't necessarily need, but here, 4 to the k over k to the k, and then raised to the 1 over k power. We use properties of exponents. This is 4 over k. Then I take a limit as k goes to infinity here of the kth root, absolute value of ak. And this is a limit as k goes to infinity, 4 over k. This limit is 0, which is less than 1. Okay, great. Now, quote the test by the root test. This series, k equals 2 to infinity of 4 to the k over k to the k converges. Number 5, term test. This one is quick. We take a limit as k goes to infinity of the terms. And this is 1, which is not equal to 0. And we conclude diverges. Number 6, we have another alternating series. And my general strategy is to first look at the terms. Do they go to 0? In this case, the answer is yes. The terms go to 0. Term test tells me nothing. But if we look here, maybe I will write this here. This series, this is what I was discussing briefly in the strategy. This, well, we can start the indices. It's fine. I'll write them. But it's a p-series. This is a p-series where p is 0.7, less than or equal to 1, diverges. Now, I'm not finished here. This gives me that if you take the absolute value of the terms, that series diverges. And so I know, for example, my series does not converge absolutely. When you get this, the next thing to check is, does the series itself, the alternating series, does it converge or diverge? And this will be an alternating series test. We need two things. We need absolute value ak plus 1 less than or equal to absolute value of ak, decreasing in absolute value. And this is true because, well, here's absolute value of ak. Okay, fixed numerator and the denominator is growing. We also need the limit as k goes to infinity, absolute value of ak to be 0. And this also holds. So by the alternating series test, we get the series itself where does this start? 1 to infinity minus 1 to the k to the minus 0.7 converges. Now, what this says is we have conditional convergence. I will write it right here. We have conditional convergence. When you have a series with positive and negative terms such that you take the absolute value of the terms, that series diverges, but the series itself converges. This is exactly conditional convergence, and we see this here in number 6. Number 7, we have comparison. So as I mentioned, I'm going to compare to this series, k equals 2 to infinity of 8 over k to the 4th. This series is a constant times a convergent p-series where p equals 4 bigger than 1, okay? So to use comparison, I need to justify that these terms are less than or equal to, here, 8 over k to the 4th. And this happens. We in fact do have this. First of all, non-negative, and the numerator is always less than or equal to 8, but also bigger denominator, smaller fraction. So I can confidently write this because we have a bigger denominator here. And we just quote the test. By the comparison test, we get this series, k equals 2 to infinity of 5 plus 3 minus 1 to the k over k to the 4th plus 3k converges. This series converges. Number 8, well, as I mentioned, I personally see a sum of two terms. I will do this in 2 steps in my actual work. First, we have n cubed over, we have n cubed times 3 to the n. And then we have 3 to the n over n cubed times 3 to the n. And both of these simplify. This is a sum. We have 1 over 3 to the n. And then plus, we have 1 over n cubed. So let's come to the side and think about each one of these series separately. We have this one, n equals 1 to infinity of 1 over 3 to the n. And then we have this one, 1 to infinity of 1 over n cubed. Okay, this one here is geometric. The a is 1/3, but that doesn't matter so much for convergence. What matters for convergence is the r. R is also 1/3. Absolute value of r less than 1 converges. Now, this one is a p-series. P is 3, bigger than 1, converges. Now let's go back to our original. Okay, the original is here. This is the sum of two convergent series, and therefore this converges. This is number 8. Number 9, as I mentioned, integral test. So we need to make sure we think about the hypotheses of the integral test. My function is f of x is 4 over x ln x. And this is, there's 3 things. We need continuous, we need positive or really non-negative, and we need decreasing. And all of these hold on here. My series starts at 3, so on 3 to infinity. Okay, very nice. Definitely this is the case. This means I may use the integral test. We want to calculate this, 3 to infinity of 4 over x ln x dx. This is substitution. U is the natural log, and du is 1 over x dx. Now handed to me in my integral is 4 over x dx. This will be 4 du. Okay, one more thing you know I always do, I change my bounds. Oh, before I change my bounds, let me write the definition. I got so excited integrating, I didn't write this definition. It's the limit as b goes to infinity of this definite integral from 3 to b. You see, I needed to write it this way to get my bounds. X ranges between 3 and b, and when x is 3, u is ln 3. When x is b, u is ln b. Okay, now I'm actually ready to have all of my side work, and I am ready to move forward with this integral. We have a limit as b goes to infinity. The integral, we have ln 3 to ln b of, this will be 1 over u times 4 du. Now I integrate with respect to u. So I still write this part. I haven't evaluated my limit yet. I have 4 ln absolute value of u, and then I evaluate between ln 3 and ln b. Okay, I'm on my very last step before I evaluate this limit. We have 4 ln absolute value ln b minus 4 ln absolute value ln 3. Okay, now here we go. This part is what has a b in it. Natural log grows without bound as b approaches infinity. So this part is growing without bound. And then we take ln of that growing without bound. So this is approaching infinity. The improper integral diverges. And so we're ready to finish the problem by the integral test. My series, which is the sum, n equals 3 to infinity of 4 over n natural log n, diverges. This is a divergent series. Number 10, and the very last one on our strategy day. Well, if you don't see this is geometric, or if you don't see the A and the R, you can always just write out your terms. So maybe let's start this way. This is geometric. When k equals 1, we have 2 over 7. When k equals 2, we have 2 over 7 squared. When k equals 3, 2 over 7 cubed. When k equals 4, okay, like this, and this continues. And now you can clearly see when we write out the terms, the A is always the initial term. Okay, this is A. And we realize it's geometric by realizing that as we move from one term to the next, we are multiplying by the exact same number. And we are multiplying by our R. So R here is 1 over 7. Absolute value of R less than 1 converges. And there's more we can say. This is one of the very few that we can actually find the sum. Okay. Usually that is not the goal. But with a geometric series, when it converges, we may find the sum. And it converges to A over 1 minus R, which is 2 over 7. Let's see. 1 minus 1/7 is 6 over 7. We invert and multiply. And this is 1/3. This is the sum of this convergent series here. This series sums to 1/3. Well, this is the end of our strategy. I hope this was helpful for you, and I thank you very much.